All right. Good morning, everyone. How are you all doing? Can you hear me in the back? No. Now can you hear me in the back? All right, cool. How are you all doing today? Good, good. I was really excited. Good. I'm good. I'm glad it's Friday. All right. Does anyone have any questions before we get started? All right, cool. I do see that our numbers are dwindling yet again. And so this is more of a message to those watching the recording, not so much to you all, because you all are here. I do warn that technical difficulties do happen. So it hasn't happened yet, thankfully, and hopefully they don't happen. But pretty much every semester, something happens to one of the recordings. So I always recommend coming, as you all are. And if you aren't able to come, have a backup plan of either planning on looking at the lecture annotations that I provide or talking to someone that is able to be here. So just a little disclaimer, because it always seems like as soon as that issue arises, then all of a sudden everyone starts coming again. So just a fair warning that there usually is some weird glitch that just happens at some point. Okay, so your first quiz is going to be this Sunday, is due this Sunday. The quiz is going to be based on everything that we cover through the end of lecture today. So from lecture 1 to lecture 5. So make sure that you do the homework. The homework is also due on Sunday. Do it before you do the quiz. But then also I do recommend, depending on how far into chapter 2 we get today, it might be worth also starting the chapter 2 homework. That way you get some of the beginning practice problems that relate. So just some advice. And then I also have posted the weekly course schedules. So you can see on the bottom of those, there are extra practice problems that are recommended. So if you want ungraded practice, there's extra practice listed out there. Cool. Now, does anyone have any questions? So, all right. Resonance, this key concept that I said we're going to be talking about all semester. Resonance is the delocalization of electron density through those parallel unhybridized p orbitals. That's why we need to know our hybridization, because you need to know how many unhybridized p orbitals you have. So you got to know what your hybridization is to know if you have those p orbitals. It is a major stabilizing effect. It is going to be spreading that electron density across the molecule. As you spread that electrons across, that lowers the energy of the molecule. It makes it more stable. It is impossible, by definition, to do it with an sp3 hybridized atom. Why? Yeah, because there's no unhybridized p orbital. Because sp3 means I took all 3 of those p orbitals and mixed them in. I don't have any unmixed p orbitals left over. So it's impossible with sp3. So I must have sp2 or sp in order to have resonance. You cannot have resonance with an sp3 hybridized atom. By definition, it is not possible. We're going to use curved arrows to show the flow of electrons. They will flow from head to tail. So our curved arrows are going to be where your head is where the arrow starts, the tail is where it points. You're going to go from where you have electrons, the head, to where you don't or have fewer. That's how our arrows are going to flow, because the curved arrow is the flow of electrons. So it has to start where you have electrons and go to where you don't. Our two-headed arrow, curved arrow, so this one, this represents the flow of 2 electrons. We're also going to have a single-headed arrow. This will represent the flow of 1 electron. Be very careful. They look super similar. They are not the same. A lot of students will make the mistake in the homework where they will accidentally grab the single-headed arrow, which is for radicals, and then get marked wrong. And they don't understand why, because it's pointing in the right direction. It's locked on. It's not pink anymore. It's gray. So everything else matches, but you picked the wrong arrow. And that means you didn't do it correctly. That means you are wrong. That's why you get marked wrong. So be very careful and intentional with that, with the arrow that you pick. This is for our flow of 2 electrons, is where it is the full head. If you have a half, then you're going to be a flow of 1 electron. That'll be our radicals. We're going to have 2, sort of 3, basic systems for our resonance structures. So the first 2, the reason I say 2 basic systems is because I want you to do the first 2 first. There'll be a third option if you don't see the ability to do 1 or 2. So it'll be like, do 1 or 2. If you can't, then consider 3. The first is going to be where we have that positive charge next to that should be a pi system. So that positive charge is going to exist in an unhybridized p orbital. That's because the only way to get 3 regions of electron density as far apart as possible is to be trigonal planar. If you're trigonal planar, you are sp2. So all of our carbocations are going to be sp2 hybridized, meaning that positive charge resides in the unhybridized p orbital. To show the flow of electrons, you're going to start at that pi bond and push towards the positive charge. You're going to put the electrons between the 2 carbons. You're indicating that the bond is moving. So we end up with now our double bond is on the left-hand side, and I just took electrons away from the carbon on the right. I took its electrons. It lost that negativity, so a positive charge gets left behind. Students will make the mistake of trying to show where the charge has moved. That's not the point of our curved arrow. The point of our curved arrow is to show how the electrons moved. The charges are just a result of bookkeeping of, all right, well, how many electrons do I actually have there? So when I take electrons away from the carbon on the right and I show that it's going over to the carbon on the left, I get this positive charge left behind. When we look at that Lewis structure, for this carbon, how many hydrogens are on this carbon? 2, good. That's going to be the only way that we can get that positive charge is if it doesn't have all 4 bonds. Remember, neutral carbon makes 4 bonds. If it's positively charged, we can't add up to 4. So the way to make that formal charge work out is going to be if we only have 3 bonds. How many hydrogens are on the carbon in the middle? 1. Remember, neutral carbon makes 4 bonds. I know it's neutral because nothing is written. I see 3 lines. Be careful, that double bond still counts as 2. So 3 lines, so there's 1 hydrogen left over. How many hydrogens are on the right-hand carbon? 2. Neutral carbon makes 4 bonds. I see those 2 lines, so there are 2 hydrogens left over. When we do our resonance structure, and we're showing that pi bond has moved over, it's important to note that we are never going to move our atoms. Our connectivity always remains the same. Do not move any atoms. If you move an atom, you've done a reaction. Resonance is not a reaction. Resonance is looking at a better picture of what our molecules actually look like. Because remember, the true structure is the average of each of our resonance structures. Neither resonance structure exists. It's the middle of the 2 that actually exists. So it's important to note we never change that connectivity. The number of hydrogens never changes. Our other major system, or major model, is going to be if you either have a negative charge or a lone pair of electrons next to the pi system. Now it doesn't even have anything written there. I really didn't like the pi symbol. So having that lone pair next to a pi system, that lone pair is going to be in the p orbital. So it is existing in that p orbital, so that is why we're going to have resonance. So that's why when I was saying assigning hybridization, watch out for if you have that lone pair, next to a pi system, this is sp2 hybridized because the lone pair is in the p orbital, because it's able to be delocalized and participate in resonance. So you have to have that unhybridized p orbital. So we're going to start at the lone pair, start at the greatest concentration of electron density and push towards the pi bond. So I'm going to take these two electrons and I'm going to make a double bond there. If I just draw that arrow, what is wrong with that? What's wrong with that product? Let's draw it. Let's draw what it's supposed to look like. Yeah. So it would be linear if this could exist. Why? Yeah. There are too many bonds to the carbon. Remember, there's one hydrogen here, right? So when I add that double bond there, that hydrogen still exists. So be really careful when you're in your line diagram. The implicit hydrogens, they still exist. They didn't move. That is now 5 bonds to carbon. That exceeds carbon's octet. Carbon cannot make 5 bonds to carbon. Carbon cannot have 5 bonds. So what we need is a second arrow going away from the pi bond, going away from that atom, so that you make sure you do not exceed the middle carbon's octet. So we're going to have a second arrow going to the carbon on the end, so that way we end up with that resonance structure. So now we haven't exceeded any atom's octet, and our molecule is happy. So we're going to draw our Lewis structures again. How many hydrogens are on the far left carbon? 2. That's how we get that negative charge. How many hydrogens are on the middle? We already talked about it. 1, still just 1. We have that double bond between the middle and the carbon on the right. How many hydrogens are on the carbon on the right? 2. So then we start at the lone pair, push towards to show that that lone pair is becoming the double bond. Those 2 electrons that were on the lone pair become the line. And then we take that pi bond and put it on the carbon on the end. It's important to recognize that it doesn't matter which of the bonds in the double bond you take, because the pi sigma assignment is arbitrary. So you can take either line. You can take the top one, you can take the bottom one, it doesn't matter, it's arbitrary. It's just whichever one you take, it'll be assumed that was the pi bond. Again, all of our atoms remain exactly as they are, that same connectivity, it does not change, but our pi bonds, that's what changed. And we took those 2 electrons, made that double bond, took the 2 electrons from the pi bond on the right, and gave them to the carbon on the right. Cool. Our third option if you can't do 1 or 2. 1 and 2 are the major. If you see 1 or 2, do that. Your third option is if you have a polar pi bond. So for example, I have this carbon-oxygen double bond. Oxygen is more electronegative than carbon. Their difference in their electronegativities is going to be greater than 0.4. We also just know from our quick assumption that carbon to carbon is nonpolar, carbon to anything else, polar. So oxygen's more electronegative, so we have this dipole moment. So I'm going to be able to take the electrons from that pi bond and give it to the more electronegative atom. Bless you. So this is only going to be considered if you don't see the positive charge or a lone pair next to a pi bond. Then you can look at polar pi bonds. All right. Looking at our general rules for resonance. You need the same connectivity. Oh yeah, what's up? Yeah, so that's exactly, we're about to talk about that. So I'm really glad you already see that. No, that's perfect. So this is not stable. So it's not stable for two reasons. One, that carbon doesn't have a full octet. We want our atoms to have full octets. We're not achieving that. Also, I have now done this charge separation. Having formal charges right next to each other, or even just having multiple formal charges, is going to be less stable. So you're absolutely right. The reason why we consider this last is because we're making a minor resonance contributor. So we got to make sure we have the same connectivity. We cannot break a sigma bond. So when I look at this, I'll frequently have students just grab a bond next door and have that hop over. And then they try to draw the product of that. What you see is two structures. I have now broken that sigma bond. I changed my connectivity. This is bad. Don't do it. There are no resonance structures here. How I can know quickly is, one, I don't see a pi bond, but also that positive charge, that is sp2 hybridized. If I see sp2, I do want to ask, do I have resonance? But when I look next door, both atoms immediately next door are sp3. sp3 is a dead stop. You cannot have resonance with an sp3 hybridized atom. So that immediately says there is no resonance. There just are no resonance structures. Cool. Do not break your sigma bonds. We do not change our connectivity. All of the atoms stay exactly where they are. All we're doing is spreading out the electron density across the molecule. Only lone pairs of electrons and pi bonds move. So the bad example is students will take that positive charge and try to show it move. That's bad. You start at the pi bond and go towards the positive. Start at the electrons. We cannot exceed the octet of a period 2 element. So our carbon, nitrogen, oxygen are the ones that we really need to watch out for. Those, we will not give them more than 4 bonds. We will not give them more than 8 electrons, 8 valence electrons. So the bad arrow would be just showing that move over and try to get 5 bonds to carbon. That's a very sad carbon. That carbon's crying. I'm not an artist. So then the good arrows, starting at the lone pair, show that the lone pair makes the double bond, but then push the electrons onto the end carbon. We need to maintain our total net charge. So the net charge of our molecules must remain the same. We're not going to create new charges. So this structure, this nitrate, has a net charge of what? 0, right? A positive plus a negative cancel out, you get a 0. So when I draw that resonance structure, I start at the lone pair. I see a lone pair next to a pi bond. So I start at the lone pair and I push over. I can't exceed nitrogen's octet, so I have to have the electrons go from that pi bond up onto the other oxygen. So the oxygen on the top now has the negative charge. The nitrogen maintains its positive charge, so that my net charge is still 0. This is good. Lastly, we are going to use a double-headed arrow, our resonance arrow, between our structures. So that's where we have 2 heads, double-headed, meaning both sides have the pointing arrow. That is telling us that our reality is in the middle of it, that we are showing that these are just pictures of the resonance structures. It's like the molecule existed, and I'm just having like rapid shot or rapid fire pictures going off. I see the one on the left, sometimes I see the one on the right, and then reality is somewhere in the middle because it all exists across it. I will frequently have students show it as just a reaction arrow, or they'll use equilibrium. These are wrong. And then they get upset because they lose points. Those are the wrong arrows. That's the right arrow. I lied to you, I have one more rule. So the resonance hybrid is going to be what indicates the average. So resonance hybrid just means mixing, like our hybridized orbitals or our mixed orbitals. So a resonance hybrid is the mixed resonance structure. It's the structure that shows the average of them. Your resonance hybrid must have dotted lines and partial or full charges. So when I look at this resonance structure, I'm going to draw my normal sigma bonds. I put in all sigma bonds, they remain because they didn't move. Any bond that moved becomes a dotted line. So because I have a pi bond in the structure on the right, on that left-hand side, I have a pi bond here, but not here. So that puts a double or dotted line on that side. And then I have a double bond here, but not in the structure on the right. So then I put a dotted line down the right-hand side. Anytime where there's a bond in one, but not in all, you put a dotted line. You can then either put a full negative in the middle to show that it's being shared across all of those atoms, to say that there is a net formal charge that goes across them. Or you can use partial charges, which is anywhere where you see a formal negative charge or a formal charge in one of the structures, you put a partial charge in the hybrid. So because I see that full negative on the left carbon, I put a partial negative on the left carbon. I see a full negative on the right carbon, so I put a partial negative on the right carbon. Anywhere where you see a formal charge in one of the structures, but not all of them, you put a partial charge in the hybrid. So those are the 2 valid resonance hybrids. As you already have indicated that you are aware, not all resonance structures are created equal. We have majors and minors. The major is whatever is more stable. It exists more of the time. Our minor is going to be our less stable. It exists less of the time. You can have more than one major. You can have more than one minor. Usually there's one major, but you can have more than one. Our guidelines, in decreasing order of priority, the first thing you need to do is maximize your octets. That is most important, especially for period 2. Make sure every atom has a full octet. So when I look at this structure, if I'm trying to draw the curved arrows, this is going to be a polar pi bond. So I'm going to take the electrons, give it to the more electronegative atom. That's how I get between those two resonance structures. Which one is my major? The one on the left or the one on the right? Left. Why? Yeah, because nitrogen has a full octet on the left-hand structure, whereas it doesn't on the right. That's perfect. So oxygen always has a full octet, but nitrogen didn't. That's what made it the minor, was that nitrogen didn't have the full octet in the structure on the right. Whoops. Oh, it's also broken. If you have maximized your octets, or there's no way of getting away from having one atom not have a full octet. So basically, there's no difference between your octets in your structures. Then you move on to rule 2, which is you want the negative charge on the more electronegative atom and a positive charge on the less electronegative atom. So when I look at these two, to get between them, I see a lone pair next to a pi bond. So I start at the lone pair and I push towards the pi bond. Between the one on the left and the one on the right, which one's the major? The left. Why? Because oxygen is more electronegative than carbon. I look to see where I get the negative charges. So I'm comparing oxygen with a negative to a carbon with a negative. Oxygen is closer to fluorine on the periodic table, so it is more electronegative. So that makes, why did I write the word left? The one on the left is your major. The one on the right is the minor. If you still don't have a clear indicator, then you are just going to try to minimize your formal charges. Usually, when you look at a structure, it's either rule 2 or rule 3 that is applicable. Like you don't, like normally only one of them makes sense, so you just pick the one that makes sense. But if it helps, you can just go in this order. So just do 1, 2, 3, and that'll get you to the answer eventually. So when I look at this, to draw the resonance arrows to get between the structure on the left and the structure on the right, I have a lone pair next to a pi bond. So I start at the lone pair and push towards the pi bond. That gets me these two structures. So my major is still the one on the left. My minor is the one on the right because, oops, there we go. Because having this charge separation is usually less stable. Having those formal charges present, we normally don't want that. Normally you want to be neutral to be stable. Why can't I start at the oxygen of the double bond, which we'll know is the carbonyl oxygen? Why can't I start at this oxygen? Go ahead and draw the results of those arrows. Look at what product you get. Yeah. Say it again. Carbon in the middle will not have more than 4 bonds. Yeah. We're breaking a sigma bond. So it would have more than 4 bonds if we didn't have the second arrow that is breaking that sigma bond. This arrow is what's saying that we're not going to exceed carbon's octet, but we're cleaving this bond. That's bad. We're not going to break a sigma bond. The product of this would be, this is bad bond angles, but I'm just going to maintain it just to keep like relative placement. That would be the result. This is not resonance. Because it breaks our sigma bond. All right, so we're gonna practice. So go ahead and try this structure. You wanna try to draw all the resonance forms, indicate which one is the strongest resonance contributor, and draw the resonance hybrid. Just do this one, we'll regroup, and then we'll do the next one. I'll give you like 2-ish minutes. And once you get an answer, or if you're stuck, just go ahead and talk to the person next to you and compare and see if you're getting the same answer. We are very quiet for like the first time. Are we doing okay? Are we not sure how to start? Okay, so we're gonna start with our model systems. So you have those 3 model systems. We consider 1 and 2 first. Which one does this look more like? Do we have that negative charge or lone pair next to a pi bond, or a positive charge next to a pi bond? Okay, so looking at this, I use the charges as my like anchor, as my like quick reference. When I look at this positive charge, it is on both of the pi bonds. It's on the atom that is directly connected to both pi bonds. That immediately negates that system, that model system. So I'm not looking at the positive charge next to a pi system. This positive charge is on the pi system. That's not it. So then I'm looking, or on the pi bond. So then I'm gonna go, okay, negative charge. This negative charge, yes, it's on a double bond, but it's also next to a double bond. So that means I'm gonna do that model system of the lone pair next to a pi bond, next to a double bond. So that means I start at the lone pair and push towards that pi bond, and I only go 3 atoms at a time. So I'm going to give those electrons in that double bond to the carbon on the end. Okay. Now draw that and see how that goes. and convince yourself that there are no other resonance structures. This is going to be the only one. I like that I actually see people talking to their neighbors now. It's a good sign. Okay, it sounds like conversations have moved off of the molecule. So hopefully that means that we now get our product. So if I am adding a pi bond between the two nitrogens, that means I'm going to end up with a triple bond, right? All my atoms start the same with the connectivity the same. So I can put in that same core or scaffold that I'm starting with. I end up with this triple bond between those nitrogens. That top nitrogen has just one lone pair, the one that I didn't touch. The nitrogen in the middle is going to maintain its positive charge. The carbon gets the two electrons, it gets the lone pair, and it's going to get a formal negative charge. So hopefully that is the resonance structure that you drew. That is the result of those arrows that you drew. Good. So then, which of these is the major? The original or the one we drew? The original. Why? Because of guideline 2. Carbon is less electronegative than nitrogen. Or nitrogen is more electronegative than carbon. So remember, this positive charge didn't move. So I'm just disregarding that. I'm looking for what is different. I see that the negative charge is in different locations. So I'm comparing nitrogen to carbon. Nitrogen is more electronegative, So that is going to be more stable, pulling that electron density and holding that electron density. So then this is my major resonance contributor. That is the minor. All right, so now we need to show the resonance hybrid. So for the hybrid, again, I start by just putting all of my atoms in place because the atoms do not move. Then I note that this double bond, that pi bond, never moved. So it also remains a full line. I have a triple bond in one that I don't have in the other. That means that I have a dotted line between the two nitrogens. I have a double bond in one and a single bond in the other. So that means I have a dotted line between the middle nitrogen and the carbon. So those are my partial bonds. For my charges, that nitrogen in the middle is always a positive charge. So it gets a formal positive charge written in the resonance hybrid. Because it's not a partial positive, it's always positive. The nitrogen on the top, that has a negative charge in one, but not in another. So then I put a partial negative next to that nitrogen. The carbon has a negative charge in one, but not in the other. So it gets a partial negative. That would be my resonance hybrid. I know that I don't have any additional resonance structures because I can't have resonance with hydrogen. Hydrogen doesn't have p orbitals at all. It's always just an s. It's in row 1. That's all it gets is s. So you will never have resonance with a hydrogen. Yeah. So the lone pair on this nitrogen gets assumed, so you don't have to draw it in. I drew it in for emphasis, and if you want to, you can as well, but you don't have to. Yep. I thought I saw another hand go up. Yeah. The nitrogen stays positive because it always has 4 bonds. So when I calculate the formal charge of nitrogen in the middle, nitrogen has 5 valence electrons. There are 4 lines, 0 dots. That's a positive 1. So because it always has 4 bonds, either 2 double bonds or a triple and a single, it always has 4 bonds, so it's always positive. Cool. Yeah.
So I'm a little bit confused about the location of one of the staggered lines, like the dotted lines. Wouldn't it be on the carbon that's directly connected to the hydrogen on the far right of the structure, or am I missing?
So I think your question is about, do you think that there's a carbon there? Okay, perfect. Okay, cool. So there is not a carbon there. The reason why there is no carbon here is because we're only going to assume the end of a line where nothing is written is a carbon. Because I see a letter, that immediately says that letter takes over. There's no carbon there, there's just a hydrogen. So that's a really good point of clarification. Yes, so this structure is just CH2N2. There's only 1 carbon. Yeah, perfect. That's a really good point. All right, do we have any other questions? All right, we're going to kick it up a notch. We're going to draw all of our resonance structures for this one. I'm not going to tell you how many there are, so you want to try to do that model system of try to consider 3 atoms at a time until you get through all of your sp2 or sp hybridized atoms that are adjacent to each other. All right, go ahead. What's up? Yeah, absolutely. Okay, so we're going to start by looking for our model system. So does it look like I have a positive charge next to a pi bond? No. If there was a positive charge, it would have to be written, so I don't get to use that one. So then do I have a lone pair or negative charge next to a pi bond? Yes, I do see that I have a lone pair negative charge, and then I'm like, okay, do I have a pi bond? Next door. So I see that there's one to the left, one to the right, and one down. So I definitely will be able to do resonance. So for that model system, it was you always started at the lone pair and pushed towards one of the pi bonds. So we're going to do the same thing. And actually, at this point, we'll regroup anyway. So we can either go left, right, or down. What do you want to do first? Right? Cool, thank you. All right, we're going to go right. So I'm going to push towards the pi bond on the right. I can't exceed carbon's octet, so I have to take that pi bond and put it up on the oxygen. So then I draw the product of these arrows. These arrows are saying, put every atom exactly as it was. Everything that wasn't touched, put it exactly as it was. I didn't touch anything to the left or down. They all stay exactly the same. But now I get a double bond between the carbon in the middle and the carbon on the right. I now have a single bond between the carbon and the oxygen on the right. That oxygen now ends up with a negative charge. I need to have, because all of these are sp2, and then these are sp, but they're all adjacent to each other. They're all next to each other. They're contiguous. They're all immediately next to each other. We need to involve those neighboring atoms as well. So you can either redraw the original starting material, original structure, and show the arrows now going to the left. Or I can start from this oxygen. I'm going to put in the lone pair that is important because I have to start at a lone pair. So I start at the lone pair, I push towards the pi bond, and instead of stopping on the carbon, which only brings me back to the original, I'm going to draw the arrows that get me to my next resonance structure, which would be where I have the double bond on the left and a single bond going up to the oxygen on the left. So I can draw these 3 arrows to directly go to my next resonance structure. So either redraw this and then just show the arrows going to the left, or you can go from this structure and push through that middle carbon to show how you would get to the oxygen on the left having the negative charge. Do not have one structure with arrows going in multiple directions, because that is saying that that lone pair is going both left and right. You can't have, like, there only are 2 electrons, so you can't show 2 going left and 2 going right. That mathematically doesn't work. Like, there just aren't that many electrons. So you would either have to redraw this structure or push through. So the result of these arrows, anywhere where my arrow points at a bond is showing that I'm making a bond. Anywhere where it points at an atom, that is showing that I am putting electrons on that atom. So I again get my same core, but now the oxygen on the left has the negative charge, and I remake the carbon-oxygen double bond on the right. So I've now used these 3 sets of atoms, but I haven't used the, not actually, do it over here. Haven't used these 3 sets where I had the lone pair next to another pi bond. So I need to also go down. So again, I could redraw the original structure, or I can start at that lone pair, push towards the pi bond. Instead of going onto the carbon, I'm going to skip the carbon and show that the bond jumps over to make a double bond. And then I'm going to take that pi bond and put it on the nitrogen. A recommendation that I make, so how I quickly used to draw structures in lecture, because I'd be trying to like copy down exactly what the lecturer wrote and then like write everything for myself. What I would do is I would count the peaks. So I'd be like, all right, I need 2 peaks. And then I would look for like, all right, double bond, double next to each other, nitrogen. So like I would count peaks to do it like quickly to know how long of a structure to draw. And then that usually helped me quickly draw structures going from a board to my page. Oh, if that helps anyone. This dot represents a carbon. You can either write a C or draw a dot. You need something there, because otherwise I can't tell if you just drew a really obnoxiously long double bond or if you meant for there to be 2 double bonds. So we need something there to clearly separate the double bonds to make it really obvious exactly what I mean. I mean that there is carbon, double bond, nitrogen. All right, so out of these, I'm going to label these, come back. A, B, C, and D. What is my major resonance contributor? B and C, good. I'm glad that you saw that there were 2. So what we're looking for is what is different. Well, the difference is that moving negative charge. So I'm comparing carbon to oxygen to nitrogen. The most electronegative of those is oxygen. So I have equal major resonance contributors. What is going to be my weakest contributor? The minor of the minors. The one with carbon, A. Because carbon is the least electronegative, so it's going to be the least stable. All right, let's get our resonance hybrid in. Put every atom and bond that didn't move in as a straight line. Everything that did move becomes a dotted line. And then you can either show the negative just in the middle to show that it's been shared out, or put a partial negative next to each of the oxygens, that carbon in the middle, and the nitrogen. And that is your resonance hybrid. Cool. Does anyone have any questions? Sweet. All right, so your quiz will be on everything through this. So that's basically just chapter 1. Have a wonderful weekend. And there's no class on Monday because it's Labor Day.